all we have left to do is the non-parametric stuff. And I just want to let you know, I haven't posted this survey yet, but I'll post it soon. And this final conflict sign-up is up. It's due online. So you can, if you're here, if you prefer to take it Friday, you can. If you, it's best to stick with your the section you're assigned to, but there's some flexibility because of this online course. I have to give them a lot of flexibility, so you guys have it too. So if you just want to, it's not a usual final. Usually with a final, you can't do that, but because we have this online section, you can. So you can just go to long cap the way you usually do. You don't have to explain why, and if you would prefer to take it, then you can. Otherwise, if you want to stick with your section, the in-people class, stick. Online people watching this, same thing. Just go there and you can switch to L1 section. You can take it either day. Any questions on that? And I'll post more about how to study and how to calculate your grade tomorrow. So we just have, so let's just get going then. And you have homework due tomorrow night, so let's start. Okay, so let's go to the document camera and begin. Okay, so turn to page 201 in your notebooks. And so we're going to start something called non-parametric tests. What is a non-parametric test as opposed to a parametric test? Well, the non-parametric tests that we're going to be doing, and most of them, all change whatever data you have to rankings, to integers between 1 and however much data you have. Like if you have 20 data points, 1 and 20. Okay, so that makes it extremely simple to do statistics on it. And it changes all the numbers to uniform distributions, so you don't have to worry about any of the assumptions that we've been worrying about. With our parametric tests, we always assume some assumptions about the distributions that our data came from. And most of the tests we've done, except for the re-randomization, assume that we're dealing with either normal populations or statistics that follow normal populations. That's the sort of underlying assumption for most of them. So in part 7, what you just had your exam on before the data transformations, we saw how you could sometimes transform data that had really lopsided histograms that looked nowhere close to normal. We could transform them to more normal looking histograms by these transformations, either basically going up or down the power ladder. That's the way to think of it. The ones we concentrated on the most were the logs. But what if that doesn't work? What if we can't transform the data, okay, to make it more normal looking? Lots of times that happens where you can't do that. So if we want to do significance tests, we have two options. When the null is that the population parameter is 0, or that the difference between 2 or more groups is 0, or the correlation coefficient is 0, it's called the strict null. When you're testing the strict null, you have, which is the null we've always been testing, we can do a re-randomization test, a resampling, and we've done those. We can do that, and you've seen, we've done that a bunch of times, where you just scramble up the numbers and just randomly assign them to each other, or randomly assign them to two groups, and then we compute p-values that way. But there's another option that we can change our numbers, whatever they are, to rankings, which are always uniformly distributed. I mean, they just have, the histogram's just going to be like just numbers between 1 and whatever n. And so the histogram's just always going to be uniform, like, like that for all the numbers, right? And so will look just completely like, so that is extremely easy to work with a distribution like that. So we can transform our lopsided data into more regular looking data by replacing values with their rankings. So for example, if I was going to do that with your exam scores, the person who scored lowest, I could say is rank number 1. The person who scored highest is rank number 100 if there are 100 people. And that's how I do it. Okay? So now we've already explored option 1. So now we're going to look at option 2. And the advantage of option 2 is that there are a few very widely used tests, non-parametric tests, that are easily calculated, and almost all statistical software has them. So they're very widely used. And so we're going to look at 3 of them. The one we're going to do today is called the Wilcoxon Mann-Whitney Rank Sum test. And what it's used for is to compare 2 group means. So it's an alternative to the 2-sample t-test. That's mostly what people use it for. Or the next one we're going to do is an alternative to ANOVA, comparing several means. It's called the Kruskal-Wallis test. And that's what we're going to do next lesson, next lecture. And the last one we're going to do is the Spearman rank order correlation coefficient. And that's a different way of, that's a rank-based way to compute a correlation coefficient. It's an alternative to the regular correlation coefficient and the standard error for that. Okay? So let's start with this, the rank sum test. And basically, you just change the 2 groups into one ordered list, and then you compute this test statistic that's the sum of the ranks. So, and then the sampling distribution from that, as long as your sample size is greater than or equal to about 6, is a z-test. So let's look at that. Let's look at an example, and you'll understand it pretty easily, I think. All right. So let's do it. All right. So this is an example taken from my experience as a teacher. This has happened to me a lot, that I'm trying to make 2 forms of the test, like of a final, that are the same. I want them to be of equal difficulty, right? And sometimes I'll randomly assign them to like people who have to take the final early. I used to do this before when I wasn't very experienced at writing tests. Now I pretty much know what's going to be the same. But I'd have to do this because I didn't want them to be of unequal difficulty for the students. And so I'd take a group who's taking it early and test it out on them. All right? So pretend I was doing that. 2 different forms of the final A and B, were randomly given to a group of 15 students. I randomly give it to the 15. You know, half of them get one form of the final and half of them get the other. So in this case, 7 of them got Form A and 8 got Form B. And here's the scores. Let's say these were the scores. All right? Now, so obviously, these don't look like normal distributions at all, and our exams are never normally distributed anyway. So and we have a small sample size, so we can't do a t-test because I know it's not going to come from a normal distribution. And I have a small sample, so here's an alternative to the t-test. All right. So the null hypothesis is the usual, that there's no difficulty in the means, no difference in difficulty between the 2 exams. And so it's actually a little stronger than our usual one. Watch, there's no difference in difficulty between the 2 exam forms for any segment of the population. Not only are their means the same, but it's not more difficult for the low-end students. For the high-end students, it's more like every percentile is the same. So this is stronger than just saying the means are the same. It's more like every percentile is the same. And the alternative hypothesis is the exam forms are not the same level of difficulty for at least one segment of the population. Maybe for the really high-end students or for the really low-end students. They're different even though the means are the same. So that's another advantage to this test. So what do? We combine the 2 groups into one ordered list. There's 15, so they're going to be numbered between 1 and 15. And then if there are any ties, you give the average of the ranks. Okay, so let's do that. This is what I mean. So what would be the ranks in this group? Well, this is the lowest score. 11 is the lowest score, so it has a rank of 1. And the next lowest score will have a rank of 2. The next 3. The next 4, but there's 2 4s. So I don't want to give them different rankings, but they take up 2 spots, 4 and 5, so I give them the average. Ties give the average, so they'll both get 4.5. Okay, and then the next one is this one. What should I give this one? You might think 5, but no, this is the 6th number. This took up spots 4 and 5, so now this is going to get rank 6. And then the next one is rank 7, and the next one is 8, and here is the next number, 9, 10, 11, 12, 13, 14, and 15. You see, you know you make a mistake if you end up at some other number other than 15, because there's 15 numbers. It has to go from 1 to 15. So this looks good. All right. And then the next thing is you really only have to figure out one of the groups, because then the other one's determined, one of the rank sum. Like, choose one of the groups and add up its ranks. That's called the rank sum. You may choose either group, but it's easiest to choose the group with a smaller number of observations. Okay, so we'll choose this one. So let's just add them up. So just add up all these ranks. And I got 56.5. So that's called the rank sum. I'm abbreviating it by R sub A for group A. So, right? That's its rank sum. And then you can do the same for this one. So we could add these all up. And I did that, and I got 63.5. So that's there. Okay. Now, these together should add up to what? The numbers between 1 and 15, this formula right here is a formula for adding up the numbers between 1 and n. And so in this case, this formula would give what? N is 15. So we have 15 times 15 plus 1. 15 times 16. Sorry, 16 over 2, which is 120. And some of you probably know this formula, where, I mean, the famous story about Gauss figuring this out when he was a kid in school and the teacher just wanted to keep him busy. So he said, add up the numbers between 1 and 100, and this is how he did it. He said, like, thought in his head, 1 plus 2, I'll just do the numbers between 1 and 15. But this is what he imagined in his head. He certainly didn't write them all out. I always thought this was a very cool story. So Gauss just pictured the first and the last, right? 1 and 100, here it's 1 and 15, and he added them together. He added those two together. In this case, we get 16. And then he took the next two, 14 and 2. He gets 16 again. He was getting 100 again. This is what he just figured out in when the teacher asked him this question. And the next one, 13 plus 3, you see how we keep getting the same number. It's n plus 1, right there. And how many of those n plus 1s will you get? Will you have? Well, half the number on your list, n over 2. So it's n over 2 times n plus 1. So 16, 16, 16, all the way down. If there's an odd number, here, 8. And you just take half of that. If there was an even, it would be the two together. How many people knew that formula? Did you know the story? It's pretty amazing. Okay, so that's, so what do we want to do? We want to check that these two numbers add up. So let's check that. So we'll check. Do those two add up to 120? And they do. So that's a good way to catch a mistake you made. Or, I mean, if you're confident, you can just, once you get this one, you can just subtract it from 120 and you know that one. All right, I mean, subtract it from what you get here. So, any questions so far? All right, and now we can use a z-stat to test the null, since for a large enough group, for large enough group samples, right, and NA and NB are both, we'll just use the cutoff 6 for this class, are both greater than 6, the probability distribution is very close to normal when the null is true. And you can see that because we're just taking the sums of numbers, and it's a uniform distribution, so the sum of so the distribution of the sum, or the average, is going to look normal very soon because of the central limit theorem. So the expected value for each group is going to be this. And you can probably see why this is true. Look, this n plus 1 over 2, in this case, it's 16 over 2 is the average. It's always the average. And this is just the sample. So another way to think of this formula is this part's the average right here. You can think of that as the average right there. And then that's the sample size. So you'd expect on the average, you know, this number's 1 below, this one's 1 above, 2 below, 2 above, etc. So another way to sum these all up is just take the average of the numbers, n plus 1 over 2, and multiply them by however many there are. And the expected value, if you randomly assign these ranks to two groups, you wouldn't expect, if it's just a random assignment, that the numbers in one group are going to end up any larger on the average than the numbers in the other. So this is just the average of the sum, n times the average here. This is the average of all the numbers. And you'd expect, why would you expect in a random division the numbers to be larger on one side or the other? You wouldn't. So if you want to figure out the expected value of the rank sum of group A, it's just going to be n for group A, which is 7, times the average, which is 8, 16 over 2, and we get 56. And you'd get the same if they have the same sample sizes, but they don't. So you'd expect the sum for B to be, because it has 8, the sample size is 8, to be 64. So that's our expected value. And right here is our standard error. And the standard error is the same for the two groups. And if you're interested in this, it's a real cool derivation of this formula, because the 12 is just, no matter how many numbers you have, this 12 is going to be here. And I'm sure a lot of you already know why. But if you want a derivation that I can post it, or if you want to see me after class. But I don't think most people want to see it now. All right, so this will be given to you on the final. So either just see me after class or send me an email, and I'll post the derivation of this. Okay, so this is given on the final, so you don't have to memorize it. These aren't, because you should understand, you know, that's real simple, but this one was given on the final. And let's just see what it comes out to be. So that's 7 times 8 times n plus 1 is 16, in this case, over 12. Okay? And it's 8.64. All right, and now, now we're just going to, as I said before, that we can calculate the z statistic here. So it's our usual, the observed minus the expected over the standard error. So in this case, what did we observe? We observed 56.5. We'll do it for A. And we expected only 56. That's not much of a difference, right? And then we're over the standard. So that's only a 0.5 difference. And that's over 8.64. So what are we doing here? So here we have our usual z curve with 0, 1, 2, 3, -1, -2, and -3. And then we'll have this rank sum for A. I'll call it RA. And with an expected value of 56. And all we want to do is figure out where our observed 56.5, how unusual it is on here. And you can, so it's 0.5 away, but where do we place it on there? Well, 0.5 doesn't seem like much, and when we divide by one standard error matches up to 8.64. So one standard error goes almost to 65 here, so it's very tiny. So as a z-score, we have something extremely small. We have what? Z equal to 0.058. So 56.5 on here. This is where 56.5 is. It's very, 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 very close to the middle. And that's where it is as a z-score. It's equal to that. All right, so we just want to get the probability. First of all, we have to look up that tiny little z-score and see what the middle area is. And what is it? Well, it's about 4%, which is approximated as about 4%. So that's between, in that tiny little strip here, it's even smaller than that, between z and negative z, between 0.058 and its negative, is 4%. And so what's our p-value? So what is p? Well, we didn't expect one exam, it's one-sided test, so we didn't expect form A to be any harder or easier. So it's a two-sided. So look at this giant p-value. It's about the biggest we've ever seen. This is so consistent with the null. So our p is what, 100? Our p is equal to 100 minus 4%, which is 96%. That's huge. The conclusion? Well, I'm delighted. It's super consistent with the null, which is what I wanted. You know, this was a case where I wanted those two exams to be as identical as possible, so I'd be delighted with this. And so it's extremely strong evidence that the exams would be fair. So I don't reject the null, of course. You don't reject the null. The null is that they're equal. So you do not reject null. Overwhelmingly, you don't reject null. This is a beautiful null. This is hugely nice evidence that the null is true. And the exams are the same level of difficulty, which is what I wanted in this case. This would be great results. Okay, and now, what if I had done ZB? What do you think would have happened? Well, let's try. So let's try ZB instead of ZA. Well, then we do the observed ZB, which is 63.5 minus its expected, and I think you can see what's going to happen. I mean, 63.5 minus 64, it's going to be over the same standard error, and we're going to get exactly the same z-score, but a different sign. And that makes sense because, however much harder one's exam is, the other's the same amount easier, right? So that would be right, this one. So this would be the positive, it would be this one. And they get the same p-value, of course. It would have a different, down here, it would have a different look to it. I mean, the same z-score. This would look like what? This would be RB, and we wouldn't have 56 in the middle here. We'd have 64. That would be 64. But then this right here would match up with our observed. So that right there would be our observed, which is 63.5. And it would be, and this one, that right there is our observed 56.5 from group A. Okay, so they get the same, so we should write that down, that ZB is equal to negative ZA. They're just opposites, and they both have the same p-values. Okay, So one thing I might want to point out to you, like when would you want to do this and what would be a huge advantage to it, and that's why I picked this particular example and why I wanted to do this test in particular, was often, like this student who got an 11 basically he would have gotten an 11 no matter which exam he took. Because somebody who gets an 11, you know what the exams are like. This Stat 100, this person just wasn't going to write anything on either exam. He was having problems. So if I included him as an 11, whichever group I put him in would look like the harder exam. But changing the rank to 1 means that he still gets the lowest score, but it doesn't weight things down. I mean, when you change it, if he had gotten what's the lowest score here? A 60. So if he had gotten a 59, it would have been the same thing. You know, somebody just gives up and leaves and just tosses the exam, they get an 11. We don't want it to ruin. It's not because of the exam, the difference between the two exams. It's because that person. So that's why in a case like this, you would really want to use this. Does that make sense? Why rankings are better than the actual score. I mean, that's not always the case. I mean, let's say this was a drug, and this is often, you know, let's say it was an experimental drug for a very serious illness or a very rare illness or something like that, and you don't have a big sample size, and this might be the length of time people live after giving the drug, let's say in months, and this 11 then it might be attributable to the drug. You might want to keep that in as let's say it's 11 days, or let's say it was 1. Maybe it kills people right away. So then you might want to for sure keep that number in. You have to think about what your data is and what it means and what you care about. But this is a great test in many, many circumstances. So let's move to another one. And this is the U test, and this is a variation on the rank sum test. And it's actually much more widely computed. For some reason, people think this is more intuitive than computing a U, so they often compute this one and convert it to a U. But I think this one's just as intuitive, and the reason why people like the U is because the tables are built for the U statistic, because it's smaller, so it's easier. So if you want to figure out the exact, don't want to do a normal approximation and look up the exact critical values to reject the null, then they'll have U. I've only seen U statistics, not rank sum. So anyways, so here's a variation on it, and some people prefer this one. I like this one better. Okay, so a variation on the rank sum test is to use the U statistic instead of the R statistic. And what the U statistic does is it sums the number of times group A scores surpass group B scores. And UB is the number of times group B scores surpass group A scores. So we'll do the same exact thing, and you'll see how they're really the same thing, a different way to figure them out. Okay, so for each number in group A, you count how many numbers in group B it outscores, and you count ties as a half. So 11. This person didn't beat anybody. Think of it as 2 teams, where everybody plays a match against everybody else, right? Okay, so this person, 11, he lost to every single person there. So he doesn't score any points for his team. So he just has a 0. Okay? And now let's look at the next one, 70. How many points does he score for group A? Let's look. Well, he beat this one, so that's 1 point, 2 points, and he tied that one. So this person, 70, gets a 2, and he gets a half for tying. So that's 2.5. We can do the next one, 75. So he beat 1, 2, 3. So he gets a 3. 85. 1, 2, 3, 4, 5. Right? Okay. 88. 1, 2, 3, 4, 5. Again. 92 beat everybody except these 2, so that's 6. And this one beat everyone except him, so that's 8. All right? And then you just count them up again. You sum them up. We can do the same for this one. So we'll sum them up. Oh, 7. There's 8 people. Excuse me. Thank you. 1, 2, 3, 4, 5, 6, 7. Yep. Thank you for noticing that. Okay. So we sum them up, and this sums to 28.5. So 28.5 is the U count. And then we do the same thing for the other one. We can do the same thing. Actually, it's easy to figure out how many there should be total. How many UA plus UB has to equal what? Well, if there's, how many pairwise comparisons are there? How many total matches are there? There's 7 times 8. So there's 56. So we know that 56 minus 28.5, which is 27.5, has to be here. But let's just check it. All right. So let's do it. So 60 beats, he gets a 1, right? 65 also gets a 1. 70 gets what? A 1.5? No, he just beats 1. 70 beats 1 and ties with him. And then 79, how many people does he beat over here? 1, 2, 3, right? And 81 gets the same number of points for his team. How many does 90 get for his team? 5. He beat everybody except for those 2. 95 beats everybody except for 96. And 100 beats all 7. So that's, so when we add these up, this is the points this team earned. That's how I think of it. And I added those up, and it is 27.5. And you can see why this is 27.5. You can see why, you know, because there's, okay, so 7 times 8 is 56. And this is true because this is how many pairwise comparisons there are. So each one of these 7 people is being compared to 8 over here. So that's 7 times 8. And each one of these 8 ones are being compared to 7 over here. So 8 times 7, it's the same. So we should check to make sure that 28.5 plus 27.5 is equal to what? 56, and it is. So we're good. All right. Now, any questions so far on this? On how to do this? All right. So now we can also, before we go on, why don't we just do some eye clickers? Okay? Just to make sure you understand what's going on. So now we're talking about rank sum, not U-stat here. That's the first one we did. Okay, raise your hand if you need more time. You're good? Okay, just everybody vote. Let's just stop it and see. Yep, 10 is the answer, so that's good. And Oh, now you're changing your answers. Did I not stop it? I didn't stop this, did I? Okay. Come on, let's get 100%. Go ahead, change your answer. It's D, number 10. Go for it. Come on. Not everybody will. There's always some people. Isn't that cool? Isn't that? There's always this, like, I think of them as mutants. Some, like, they just started, or maybe just, mutations are not necessarily a bad thing. Okay. Yep, they're always there. Okay, we're stopping it. I've never gotten 100%, I don't think. And let's just see. So let's look. And yes. This has to get out of the way so you can see the answer. Why? Because it's one, you have the ranks 1 plus 2 plus 3 plus 4. Does everybody understand that? The lowest you could do, it's what the most extreme would be the 4 lowest people in that group, and it would be 1 plus 2 plus 3 plus 4. So the sum would be of that is 10. Does everybody understand? Let's do the next one. And let's start this one. What's the highest? Okay, I'll just give you a minute, then we'll stop it. Okay, a few more seconds. Great. That's the answer. 26, great. And let's look why. Because you just add those up. All right, now let's do the next one. And how about this one? Everybody have enough time? Okay, I'll stop it in 2 seconds. So just vote. And let's stop and look. Great. Yeah, the answer is 0 because if you put all those 4 lowest ones, they have a rank of 1, 2, they'll have a rank of, it doesn't matter how many are in there. They'll all be the lowest people, and they won't beat anybody. So they won't score any points for their team. They'll all have U counts of 0. Does that make sense? All right, and you know what the next question is going to be then. What is the highest possible U score either group could have? What? Oh. Oh, there. Look what I did instead. Oh, just click on it. Just here, I'll open it so you can click on it and you can vote. Why is this? Oh, sorry. too bad that I didn't get a chance to get a feel for that one. But you can see that, think of it as just that there's 20 matches. So let's see if everybody got it right. This is so funny. Okay, let's just check this out. Yay! Woohoo! You deserve it. Okay. All right. But you understand why. That it doesn't matter that there's an uneven number of people in the group. In each group, they just won all the matches. All right. So I think you understand this pretty well. Let's go back to the notes. Okay. So now we can also do the same thing we did before. We can compute a z-statistic, and we're going to get the same answer. All right, and so let's see. So we can use the z-stat to test the null the same way. And here, the expected value of UA is equal to the expected value of UB. They don't have to be the same size. And they're both equal to the number of pairwise comparisons. So in this case, it's 7 in one group times 8 in the other, divided by 2, which in this case is 28. And that makes sense because you'd expect half the matches to be won. If each player plays every single player on the other team, that's how you can think of it, you'd expect half the matches to go to one group and half to the other. Even if there's only one person here, he's good. Like if the expected value is that person would be in the middle of the pack, so would win half the matches. So it doesn't depend on how many people are in either group. Does that make sense? Okay, so we have that, and the standard error is exactly the same as before. 7 times 8 times 16 over 2, which again is 8.64. All right, so it's no surprise that this is the same because because they just differ by a constant. Remember how I told you that most people figure out the rank sum, then there's a formula to get the rank, to get the other one. They don't use this simple formula, but you can see that they just differ by a constant. You can see, for example, that UA was, in this case, 28.5. And the constant, think of it, when group A has all the lowest numbers, right, then UA is equal to 0. And the rank sum for A would be what? Just 1 plus 2 plus 3, however numbers are in group A. That's what we just did. Remember, we saw that the rank sum for the lowest group was 1 plus 2 plus 3 plus 4, but the U statistic was 0. So they differed by 10 there. Here, the U statistic is going to differ by, this is 28, because 1 plus, what is it? I'm just adding up those numbers. Remember, for it's going to be 7 numbers in A times n plus 1 is 8 over 2, and that's 28. So this right here is 28. And that's equal to 56.5. So this is UA plus the lowest number. The number, that's the constant you'd add to convert to the other one. Because does that make sense to people? I don't know if I explained that well. But you see, basically, when everything's, that's the iClicker you just did. So you don't have to remember that or anything. I'm just saying this is very convenient. All you have to do, this is going to be given to you, and that's just what you're going to use for all these, for both of them, for the standard error. And you don't have to memorize that. And if you're interested in the derivation, I'd love to show it to you, and just email me or come after class. Okay? No? Okay. So now, so what do we want to do next? All right, so you're going to get the same z-stats, and I think you can see that. because here, what do we have? We have the observed U minus expected. So they just differ again by 0.5, and it has the same standard error. Right here's your standard error. So we're going to get the same thing. Okay, so that's 28.5 minus 20 over 8.64. So again, it's just that little difference of 0.5, and we get 0.058. And it's the exact same thing. The picture's just a little simpler because here you have Z, and here you have the expected value for both the U's. The expected value is the same, which is 28. And UA is right here at 28.5. And it turns out to be a tiny little, that's 28.5. And that's equal to Z for UA. And the other one's going to be 27.5 here. That's not Z, that's the actual UA, sorry. That's very messy, but that's the actual. This is the actual U's. So that's UA and that's UB. And this is Z for UA, and this one's going to be Z for UB, right? We can, here's UA, we can do, it's the same thing, it's just, where is it? 27.5. So it's just going to be 27.5 minus 28 over 8.64. So it's negative 0.058. That's ZB. And they're opposites again. The same as for the ranks. And the p-value is the same. That's 4%. We just did it. And so it's 100 minus 4 is 96%. And everything's the same. Do not reject null. The U-stat is featured in a lot of other things under different names. If you've ever looked at rock curves, that's sort of based on U-stats. You'll see it a lot. Okay, so any questions on that? So now the U-stat is the one that you use to look up, excuse me, the U-stat is the one you use to, if you didn't want to do a normal approximation and you wanted to actually find the critical value on a table. So let's do that. On the next page. So these tables use the exact probability distributions, which are easy to do because the numbers are so simple. So for small sample sizes, instead of using the Z, instead of using the normal curve, it's not such a good approximation. But that's not a problem because you, when you convert data to ranks or U-counts, the numbers are simple enough, so it's not very hard to calculate the exact probability distribution for small samples by hand. And more conveniently, there are these tables available. And all the ones that I've found look like this. They're for the U-stat, at least the ones that I found in books, but not for the rank sum. So most people use tables to find critical values. All right, so now, so this is a one for the table for alpha equals 0.05, okay, and it's for a two-tail test, equivalent, like, you know, same thing as 0.025 for the one-tail test. All right, so let's look at this. So N1 and N2 are the sample sizes of the smaller and the larger group. So we want to look at 7 here for us, right here. That's our smaller, and here's our larger. And that will give us a critical value right here of 10. And these are the critical values for the smaller one. You know, it's symmetrical. It's the smaller one. They're just using this is for the smaller one. So if R U statistic for our smaller group is less than this, then we'll reject the null. Ours is a lot greater. So let's write that down. Okay, these are the critical values for the smaller, right? So you want to compare our U stat to the critical value. All right. So for these, if the lower U stat, just look at what you got in the one that's smaller, is less than the critical value here, ton, you'll reject the null. But ours was bigger, so we're not going to reject the null. Okay, so our, let's write it down here, our lower U stat was what? It was actually the one with the bigger number of, our lower one is UB. It's 27.5. And that's not less than U star equal to 10. So we cannot reject null. Okay? So cannot reject null. And we didn't reject the null. We didn't want to reject the null. That says cannot. Okay, so any questions on that? Let's see what else we have to do. How about, why don't we skip this? This is just for fun. This is not something, I just said rearrange the exam scores to find a U stat closest to the critical value without going over. So you can play around with that one. It's kind of fun to do, just to rearrange them to see if what one would give you the lowest and so forth. So this is just for fun. Do on your own. If it's not fun for you, you don't have to do it. Okay. If it's miserable for you, don't even try. Just for fun. I like doing stuff like that. That's why I put it there. Okay. Now, last page, and then we're going to go home for today. Okay. So I said that, you know, a strong point of these, this Wilcoxon Mann-Whitney test is that it compares the whole distribution and not simply the means or medians. This means that two different distributions could have the same mean or median, but the Wilcoxon Mann-Whitney would reject the null. That's unlike the two-sample T that just looks at the means. All right, so look at the distributions below. In both cases, they have the same mean, but different distributions. Would this test reject the difference in distributions in both cases? Well, if it's symmetric around the mean and looks pretty much the same, it's not going to reject it. So no for that one. And when it's asymmetric, it can, yes, it will. Or it could. Not always, but yes, usually. All right, so let's give an example, and then you can see what I mean. So let's do a symmetric around the mean. So if it's symmetric around the mean, it might not detect it. So let's do this one first. So symmetric. And I just made up a super easy example. I just did group A, which has the numbers -1, 0, and 1. And then I had group B, which has these, also has a mean of 0. So it's going to be in the middle, and it's going to be symmetric, but I'll put it -2, 0, and 2. So they're different. All right, this is going to be the same. You can probably see that the rank for both of them is going to be the same. What's the rank for this one going to be? This is going to be what? This is a 1. Those are the numbers. Here's the ranks. This is a 1. This is a 2. This is a 3, that's a 3, so they're both going to be 3.5. This is the next one, 4 and 5. So when we add them up, plus, we get 10.5 here, and we get 10, no, I did this wrong. Did we get there's 6 numbers. I knew that I had to do it wrong. Yeah. See, that's a good check. There's 6 numbers. So look what I did, and not on purpose. Just what I told you not to do. These two are tied, 3.5. So they take up spots 3 and 4, don't they? So what? I shouldn't take a 4. This should be what? This is the 5th number. And then what's this one? The 6th one. I have 6 numbers. Check your last number 6. And I didn't do that. That's a common mistake. Does that make sense? I'm so sorry. So that's the same. It looks like a child wrote that. All right. Oh, I'm young at heart. Let's try the next one, the U. Let's try that one. What would the U be? Okay, so the U, this -1, higher than any of these? Is it? So it gets how many points? 1. Higher than that one. 0. Higher than that one and tied with that one, so it gets 1.5. And 1 is higher than that one and higher than that one, so it gets 2, right? So we add those up, and what do we get? Is that right? 4.5. All right, we should get the same thing here. Let's see. This one scores a 0. How many does this one beat? That one, and so it's a 1.5. And then 2 beats all of them, so it's a 3. When we add those together, we also get 4.5. So yes, these are, and oh, let's check we did it right. These two, we could have, another way to check we did it right is what? What would be the check? 10.5 plus, well, first of all, this one plus this one, you could check that UA plus UB has to equal what? 3 times 3. Does it? Yes. And we should check just to, that what? RA plus RB, oh gosh, what should it equal? You tell me. How many numbers? 6 times 6 plus 1, which is 7, over 2. N times n plus 1 over 2. And that's what? 21. Does it? Yeah. That's good. So it does. But did it detect that these aren't the same exact distribution, but did it detect it? No. It says they're exactly the same. So how about if they're asymmetric around the mean? Let's do the same mean of 0. So this is an example with asymmetric. Same mean equal to 0. This has the same mean equal to 0 too. Between the two groups equal to 0. But now it's going to be able to detect it. Okay, I'll do the same one, -1, 0, and 1. But now I'm going to do a really asymmetric one. I'll do -5, and then I'll have 2 and 3 here. And that sums to 0. So they have the mean of 0. All right. So now this is the same. We have 10 points. Oh, no, we have to do it. It won't be the same, will it? Because we have to compare it to all that, don't we? It won't be the same. So what will be the rank? Let's do our rank. So this one, why don't we just write the rank? So this is the lowest, and then this is the second lowest. Tell me if I make a mistake. The third, the fourth, the fifth, and the sixth. Is that right? Did I do that right? So if we add those all together, what do we get? We get 9 here, and do we get 9 here? No, we get 12. So here they're different. So it can detect a difference here. See, they're not the same. Does that make sense? I just wanted to show you, why am I writing it like this on a number line? I wanted to show you like their history. It's a different distribution. How about, and we can check again, 9 plus 12 is 21, so we did it right. Let's do the U. So the U, all right, so -1 beats -5 and nothing else. 0 beats -5 and nothing else. And 1 beats -5 and nothing else. So we get that equal to 3. Here, -5 doesn't beat anybody, and 2 and 3 both beat everybody. And again, they add to 9, so we know we did it right, didn't we? But, so let's just sum it up. So these are different. So, this type of test, that's what it's called, the Wilcoxon Mann-Whitney test, the U-test2 test doesn't detect differences in distributions with the same mean if they're symmetric around the mean. But it does if they're asymmetric. Also median. It's even easier to see with a median. Oops, I spelled that wrong. That says asymmetric. I know, it sounds like a dirty word. It's asymmetric, right? I spelled it wrong up here too. Put another M in here, jeez. Okay, anyways. Okay, but the test does detect differences in asymmetric distributions with the same mean. So it's a cool test. So I think that's it for today. And you have homework. So you're welcome to stay and get your homework done, or I can help you with it for the next 15 minutes.